Welcome to T1, Day 7 of Honors Precalculus. Today we're going to talk about logistic functions, and yes, your test is going to be in about 3 class periods. It's already in Veracross. So logistic functions are related to exponential functions, where we specifically have this need to look at functions that grow initially like exponential functions, but then they even out, like things like growth of seedlings. They start growing exponentially, and then they flatten out, slows down to a horizontal asymptote. These are called logistic functions. They have these two forms, here, and you need to memorize them. You'll notice that there are 2 exponential functions embedded right there, 2 that we have seen before. So the first thing we need to understand is what these look like in general, and there's really 2 cases. The first case is going to be when b is between 0 and 1. And when we look at end behaviors, we're really looking at the limit as x goes to infinity of this entire function. And specifically, there's only one place where there's x in it, which is right there. So we're really interested in knowing what's the limit as x goes to infinity of ab to the x. Well, if b is between 0 and 1, when you raise it to successive powers, it gets smaller. So this thing is going to get smaller. A is static, so this whole thing is going to go to 0. Static means unchanging. So this right here is going to go to 0, so this whole thing is going to go to 1 over 1, which is 1. Now, the other direction is the limit as x goes to negative infinity of the same thing, ab to the x, a times b to the x. And the key thing here is that b, again, is between 0 and 1, but x is going to negative infinity. Keep in mind, when something is a negative power, it flips what's inside. So if you want to think of b as 1/2, for example, to the negative third, that's the same thing as 2 over 1 to the third. Changes to positive, and you flip over the fraction. So what's going on here is you have something that's between 0 and 1 flipping over, becomes something like 2, and then you're raising it to a huge power. So if you're looking at the limit as x goes to negative infinity of ab to the x, this is going to get really big. So this thing is going to go to infinity. So if this thing goes to infinity right here, 1 over something huge is going to go to 0. So what that means is when you have b between 0 and 1, when you graph these, here's what the end behaviors look like. As x goes to infinity, it goes to 1. So you have it going like this. It's approaching 1 like that, y equals 1. But then as it goes to negative infinity, it goes down, concave up style. We're going to examine what happens in the middle, but now we just know it has 2 different horizontal asymptotes depending on which side you go to. Now, I said there's a second case, and that's when b is greater than 1. I like to write it like this if you can. Now, the only thing you need to know here is that the algebra flips itself. You can do the same steps you did up here, and what ends up happening is instead it goes like this if b is greater than 1. It's going to be concave down here and concave up there. But it approaches y equals 1 going to the left this time, and y equals 0, the x-axis, going to the right. It flips over. So what happens if we wanted to graph a specific logistic curve? Well, let's find y-intercepts, which is when x is equal to 0. Plot some points. So in that case, you're plugging in 0 into the function, so it's 1 over 1 plus 2 times 2 to the 0, which is 1 over 2, I gotta slow down my writing, take my own advice. 1 plus 2 times 1, because anything to the 0 power is 1. So that's 1 over 3. So the y-intercept is 0 1/3. We'll plot that, and we'll make that 1/3 right there. So if that's 1/3, that will be 1 right there. So we know there's a point right there. What about the end behaviors? Well, that's totally dictated by this, the 2 value. That's the b value. So in this case, b is 2, which is greater than 1. So it's going to look like the second function form, which means it's going to look like this. So to the left, it's going to be curved like that, and to the right, it's going to be curved like that. And we know it goes through 1/3, so we can just keep it going like this. And like this. But we want to know where it changes concavity, and it doesn't necessarily change concavity at that intercept. That's what we're going to look at. So in this case, we know that the limit as x goes to infinity of y, it goes to 0. That's the green. And the limit as x goes to negative infinity of y is 1. I'll clean that up just a little bit for you. Hold myself to the same standards I hold you to. That's the yellow behavior to the left. So we're almost there. We want to know what happens in the middle. The point of inflection is where it changes concavity. And here's the key. It happens in this specific case with this specific type of function halfway between the horizontal asymptotes, which means that halfway, which is 1/2, it happens right there at y equals 1/2. So we just need to solve this. 1/2 equals the function 1 over 1 plus 2 times 2 to the x. You solve this by cross multiplying. So 1 times 2 plus, equals, not plus, equals 1 times 1 plus 2 times 2 to the x. So that's 2 is equal to 1 plus 2 times 2 to the x. Subtract 1 from both sides, and you end up with 1 is equal to 2 times 2 to the x. Divide by 2, 1/2 is equal to 2 to the x. 1/2 is 2 to the negative 1. And for this to be true, negative 1 has to equal x. So x is equal to negative 1, which kind of makes sense on this picture. It's not quite to scale, but we know that it's going to be concave down to here, and that point right there is negative 1, 1/2. What this tells us, and it's going to ask us this later down on the page, it's concave down all the way to there, and then I'll change highlighter colors, and then it's concave up past the point of inflection. So it's concave up from negative 1 to infinity, and then it's, let me see if I can get this right. Let me get this back here. Try to get it back. I'm trying to get it back. Can't get the right color, but I'll try. This one right here, the red, we'll call it red right there, concave down negative infinity all the way to negative 1. It happens because the point of inflection is halfway between the horizontal asymptote. So that's concavity. What about boundedness? Is there a ceiling? Yeah, the yellow line, which is y equals 1. Is there a floor? Yeah, y equals 0. So it's bounded above by y equals 1 and below by y equals 0. Yay. So one thing you're going to have to get good at is graphing these by hand. You will be able to check them with your calculator, and it notes up here, I think you need to graph it on your calculator. You can check that. Please know how to do it on your calculator, please. But we need to know how to do this by hand. The first thing you look at is this 15. It's no longer 1, so that's where the ceiling is going to be. That's where the ceiling is going to be on this. Meaning instead of a horizontal asymptote at 1 and negative 1, it's going to be at 15 and 0. So we'll just put 15 all the way, let's put our scale in here. Let's put the scale in. Let's say 5 is here, 10 is here, and 15 is here. And here's the b value. The b value is 1.3, which is greater than 1. So it's going to go to the left up here, and it's going to go to the right over there. And we know just from the b value, it looks like this. So let's find our intercept first, y-intercept. To find the y-intercept, that's when x is 0. So y0 is equal to 15 over 1 plus 2 times 1.3 to the 0. This right here is just 1, so it's going to be 15 over 1 plus 2, which is 15 over 3, which is 5. So the intercept is actually right there. So we can extend this curve right there to go just like this. Yay! Now, though, we want to find the point of inflection. We want the point of inflection, and we do that by finding what the y value is at the halfway between 15 and 0. That right there is going to be 7.5 right here. So this right here, 7, oh, I dotted it a little too low there, like that. Y equals 7.5, which is 15 over 2. So how do we figure that out? We set it equal to 15 over 2 to find the point of inflection. So you're solving this. 15 over 2 is equal to 15 over 1 plus 2 times 1.3 to the x. Now, you can do this algebraically in a similar fashion, but because it's 1.3, when I say similar fashion, I mean similar fashion to the last one we did. That 1.3 makes it a little gnarly. So what you can do instead is use your calculator. You can plot this on your calculator and plot y equals this one on your calculator and plot the intersection to find this point. It's going to go, and I'll try to draw this curve a little bit better here. It's going to go like this to there, and then it's concave up here. So that curve, we can do this curve a little better here. It's still going to be concave up. It's smooth. It shouldn't have any quirks to it. So it's concave down to the point of inflection, and then concave up past it. So if you plot this on your calculator and plot the intersection, you can use logs to find it if you want to, and we can do this out, but you need to be able to get to the point where you plug it into your calculator or do it by graphing. I'll show you a little bit of it. So you end up with cross multiply here, 30, because that's 15 times 2 equals 15 times 1 plus 2 times 1.3 to the x. So divide by 15, 2 is equal to 1 plus 2 times 1.3 to the x. Subtract 1, 1 is equal to 2 times 1.3 to the x. So now you have something similar to what you have before. 1/2 is equal to 1.3 to the x. The challenge there is that you can't do that without a calculator. That's in log form. Sorry, that's in exponent form, so you need to go to log form. And if you go to log form, it's going to be log base 1.3 of 1/2 is equal to x. And then you have to use change of base, so that's log of 1/2 over log of 1.3 is equal to x. And if you do that on your calculator, it comes out to be about a negative 2.642. So the point of inflection here is negative 2.642 comma 15 over 2, which is 7.5. And now you can answer all these other questions, like where is it concave down? Well, it's concave down from negative infinity all the way to negative 2.642. And it's concave up from negative 2.642 onward. In this next example, I'm going to leave it to you to do out. The key things to look at are what's the b value and the 100. That starts you out. But you do it out just like we did. So on this next one, it's going from the graph to the equation. So we're going to know that we're finding this. Y equals 1 over 1 plus ab to the x. But it's not actually 1 because the horizontal asymptote is occurring at 50, so we can already plug in 50. So to answer this question, we need to know what does a equal and what does b equal, and we have 2 points. We have 0.25 and 120. You plug those in to solve for each of the values. You plug those in to solve for each of the values. So for example, 0.25 means when you plug in 0, you get out 25. So 25 is equal to 50 over 1 plus ab to the 0 power, but anything to the 0 power is 1. So this is 25 is equal to 50 over 1 plus a. So that means that 25 times 1 plus a is equal to 50. So that means what we end up with is, divide by 25 and you get 1 plus a is equal to 2, so a is equal to 1. So now we know that y is equal to 1, sorry, not 1, 50 over 1 plus 1 times b to the x. So we need to solve for b. How do we do that? We plug in our next point. So we know we get out 20 when you have 50 over 1 plus b to the 20th. And by that I mean b to the first, sorry, because the point is 120. So you get out 20 when you plug in 1. It's a lot better than b to the 20th. So if you cross multiply this, you end up with 50 is equal to 20 times 1 plus b. Divide by 20 on both sides, you get 5 over 2 is equal to 1 plus b. So b is equal to 5 over 2 minus 1, which is 5 over 2 minus 2 over 2, which is 3 over 2. And you can write that as 1.5. So the final answer to this is 50 over 1 plus 1.5 to the x. All you're doing is solving for a and b with 2 points. Please also take some time to work out the next 2 examples. They are very similar and rely on what we just did.